There are a ton of videos on YouTube of people attempting to make their own versions of this using things like belts and 3D prints and stuff like that. Many of them fail because these are fairly high precision devices and the loads they experience are pretty high. This is the first one that I've seen that is commercially available for what I would consider a reasonable price. Typically, Harmonic gearboxes are like $400. This all in at the time of writing is $125. So depending on how you think about it, this is either a really cheap Harmonic gearbox or a very, very expensive stepper motor. Harmonic gearboxes tend to be popular because they have a very high ratio in a pretty small package. This one here is 30:1. It's rated for 3 Newton meters of torque and supposedly has 2 arc minutes of backlash, which is incredibly small. Having a lot of torque and having very low backlash are both highly desirable in pretty much all robotics applications. For this video, the plan is to do some really basic testing. I want to look at the accuracy of the motor, both loaded and unloaded. I want to look at the torque of the motor, holding torque, continuous torque, and kind of what happens if I overpower it. And then I plan on opening it up to kind of see how it works and how they've decided to construct this one. For all of these tests, I'm using this Things by Josh component. This is an open source project that uses an ESP32, a TMC2209, closed loop kind of encoder feedback, and USB PD, so I can pull 20 volts from a wall charger with this thing. It's frickin' awesome, and the best way to support open source projects is to pay for them. So I bought at least 2 of these from the guy. I'll put a link to this down in the description, Things by Josh. And if you purchase one, let Josh know that I sent you over there. Generally, in robotics, steppers are popular because they are inexpensive and they allow you to pretty much command a position, and assuming the torque of the motor is sufficient, that you can assume comfortably that the stepper made it to its position. Steppers are designed generally to run at a low speed, so tens or hundreds of RPM, with a very high degree of positional accuracy. So to control a stepper, you step through positions, rotating the shaft from one locked position to the next. Gearboxes sit between the stepper and the output and further reduce the RPM, while in theory increasing the positional accuracy. Primarily, 2 things can cause positional inaccuracy in a gearbox: backlash or lack of rigidity. Backlash is the space between the teeth of a gear. In an application that requires positional accuracy, having any sort of gap between gear teeth means you don't actually know where the end effector is, only a zone between the teeth that it might be in. Minimizing backlash can be expensive though, because it necessitates holding a very tight tolerance in the manufacturing and assembly steps. Rigidity is how much deflection is caused by applying a force. If you made a gearbox and used rubber teeth, it would appear to have 0 backlash when unloaded, but that's not the full story. When you applied a varying load, it would be hard to determine its actual position because the gears would be flexing, kind of defeating the purpose of a gearbox. Of the 2, backlash is a larger issue from a control standpoint. It shows up as a nonlinearity in the control algorithm, which can make it very difficult to account for where the stepper is pointing without just guessing. For both backlash and rigidity, we can actually just use the same test. I'm going to lock the stepper in a position and apply both a clockwise and anti-clockwise torque to the output. The measurement we see is going to be an accumulation of all of the parts between the stepper motor and the part that we're measuring flexing. I've done my best to make it so the gearbox should be the most flexible part of the assembly, but everything is a spring. To measure the stiffness of the gearbox, we can just look at the deflection versus force graph. We know that springs deform roughly linearly, so we expect the graph to be a line. Backlash would present itself as a flat zone between 2 straight lines, showing that there is movement even when there's little or no force. Looking at the graph that we got, you can see that there's kind of a nice linear section on either side and then a little bit of a dead zone in the middle. That dead zone is the backlash, and it appears to be within the realm of what we expected, about 2 arc minutes. To actually make these measurements, these are incredibly small distances. The stated accuracy of this gearbox is 2 arc minutes, and this is incredibly tiny. If you imagine a circle, you have 360 degrees within that circle. Within each of those degrees, there's 60 minutes. And then if you want to go even further, there's 60 seconds per minute of a degree. To state it in a different way, the angle we're trying to measure is roughly 0.03 degrees. Typically, when you're measuring something like an angle, you use a protractor. The problem we're facing with this is the tick marks between the arc minutes on a 4-inch circle would be roughly the size of a white blood cell. To make the measurement device we're using more sensitive, we can increase the distance from 4 units to something much larger. For this specific test, we went up to 315 inches, which gave us a much more reasonable 2 millimeters for a backlash of like 2 arc minutes. Now, if we take a laser and bounce it off of a mirror that is 315 inches away to measure the backlash and the stiffness, the distance that we're looking for, instead of being the thickness of a white blood cell, is a few millimeters, which is much easier to measure. Since this is an accumulation of all of the components flexing outside the shaft, I don't think we're actually going to be able to accurately measure the stiffness of the gearbox assembly. But we will be able to see the backlash showing up as that nonlinearity. Just for sanity, I attempted to do the same thing with a normal NEMA17 without a gearbox. It was so weak, I couldn't even get an ankle measurement. Even just lightly brushing it with my finger was giving a massive displacement on the far end. So as far as I can tell, this holds up to the 2 arc minutes that it is spec'd out to see. So I would expect 2 arc minutes, maybe a little bit less, and then the deflection after that kind of comes down to what your robot is built out of. Torque is essentially a pushing force, but in a rotating direction. Now, steppers are a special kind of brushless DC motor wired specifically to maintain a known position at low or no speed. The torque of a motor is at its maximum when it's stalled. This torque then reduces as the speed increases. Plotting the relationship between torque and speed is called the torque curve. For most motors, when they're fully stalled, they're going to pull a ton of current, and this can quickly overheat and damage them. A stepper, on the other hand, is wired in such a way to generate the most amount of torque per amp. Then you control it using current limiting circuits, which step through a sequence of positions to move the rotor. The consequence of this, though, is that they tend to lose their torque very quickly as the RPM goes up. A normal motor will have a pretty flat torque value up until a few hundred RPM. Stepper motors almost immediately start losing torque. So their peak torque is when they're fully stalled, and as you increase the speed, they pretty linearly drop off. The proper way to design for a stepper motor is to pick a speed that you want to operate at, and then choose the motor that has sufficient torque to accomplish the task. The challenge with that is it's pretty limiting. It pretty much narrows you down to one type of motor. Using a gearbox increases your options because it allows you to select a speed and torque from a smaller class motor and generally just have more options. The trade-off is you're reducing top speed, but steppers are already not very good at that, and depending on the application, you can get away with a much smaller motor than you'd otherwise need. Measuring the torque is pretty straightforward. I used a torque wrench with a digital readout. I ran the motors at a low speed, simulating their holding torque. This one peaked out at more than 5 Newton meters of torque to get it to stall and skip steps. The normal, so an ungearboxed NEMA17, struggled to hit 0.4 Newton meters of torque. So this is a massive increase, more than 10x the available torque. To test the continuous torque, I essentially just turned up the speed and performed the same test. This one stalled out in the kind of mid-2 range at higher speeds, while the other stepper, the NEMA17 stepper, again peaked out at more 0.2. So again, kind of an order of magnitude difference using the same exact stepper, same input power. So in the next part of this video, I'm going to take this guy apart. We'll go through kind of how it goes together, what's on the inside of a harmonic gearbox, and talk about kind of how it's constructed. So this is the harmonic gearbox. On the front, it appears to be all aluminum parts. This one is colored black, but I've got my suspicions just on how it feels that it is actually aluminum. So if I take this and try to scratch it, that's definitely like a black hard coat or something. It's not. When I first got it, I thought it was Delrin or plastic, but it feels way more like aluminum. If I come in here though and undo these, I've just got this blue mat here to take up grease. So looks like on the front of it, it's a nice little gearbox, comes off cleanly. I'll get in there and open this up, but we've got a bushing and what looks like a pressed on piece. This just transmits torque and gives a little bit of compliance. to it. So put that aside. This guy, let's see if this pops off. Yep. It's just a flange. And then here's the harmonic elements. So if I spin that, you can see it spins around. Nice. So you can see here, if I press that out, bushing, and then this is the actual harmonic element. This is a eccentric bearing of some kind. And then in there, got a handful of screws to take out. All right, so looks like I've got the, oh, there's one more part in there. There we go. So I've got the harmonic kind of flexible coupling. Looks like there's a little bit of a strain relief or flexible element in there molded into it. These are all injection molded parts, so the economics are probably pretty good. But it appears to be a steel ring gear with a 6904Z bearing in there with the interface component pressed into it, and the bearing is pressed into the silver housing. And I believe the steel is probably pressed into both of them to lock them together, because I can't separate those. On top of that, there is a shim, probably just to add some space, and there is the harmonic cage, which lines up with the screws that go in. I'll just assemble this while we're talking about it. There's this metal plate, which probably just helps transmit some torque and make it so the plastic isn't taking the entire load. This, I'll press it in while it's outside of the housing, just because it'll probably be a wee bit easier. You can see here, if I press it, I'm rotating it just by squeezing it. That's kind of how it works. In installing this, you want to line up the high points, essentially. That goes in. This presses down to retain all of that. And this guy goes in to couple it. And if you wanted to outfit this on a bigger stepper, you would just have to replace this little black piece to whatever size shaft you want to use. So that would be an idea. You purchase this and then maybe 3D print this part, since it's plastic anyway and seems pretty low tolerance. But this guy goes in, and that connects to your stepper motor. And then these guys go in and just connect it all together. But in conclusion, this is an awesome package. For 125 bucks, you've got a NEMA17 stepper motor that performs like a NEMA34 stepper motor. This one comfortably has the 2 arc minutes that's advertised. The ability to hold 5 Newton meters of torque when it only is advertised as holding 3 Newton meters To put that in perspective, this is roughly 1.7 by 1.7 inches. The size of the stepper required to do that without a gearbox is 3.4 by 3.4. So, you know, much, much, much larger stepper would be required, and the associated weight. So the ability to get 5 Newton meters out of this little tiny package is awesome for most robotics applications. If you have any questions or want me to run this through any other tests, let me know down in the comments. Other than that, I'll see you in the next one. Thanks.